Principles of Operating Systems, Chapter 2, Characteristics of Operating Systems. A computing system requires a set of resources to process and move and store the data. Among these resources, a central processing unit to do the processing, computer memory to store the data and program code, file storage, input-output devices, and network connections, all involving input-output, and a system of buses to move data from one resource to another. An operating system manages the resources and provides interfaces for coordinating and transferring the data, for coordinating the use of the resources. An interface is a boundary, a connection between two or more separate components of the computer system that allows the information to be transferred from one component to another. The operating system manages and coordinates the system resources. In addition, it provides interfaces for communication between the users and software, users and hardware, users and peripheral devices, software and hardware, software and peripheral devices, and hardware and peripheral devices. Now, the earliest of the operating system, the priority was efficiency or speed of execution. And the way they measured this was simply to measure how long it took to execute or process a single program. When they developed systems that could load more than one program into RAM at a time, they started changing the priority system in their design of operating systems. Changing it, instead of just concentrating on how to get one program executed quickly and efficiently, they started counting the number of programs that could get done in a given period of time. Then, with computers bigger and faster being used for more and more different kinds of things, they started taking other kinds of factors into consideration when they were designing their operating systems. Factors like convenience of use, ease of use, portability of the system and products, stability of the system, and security. The core part of the operating system is what's called its kernel. That's a computer program that forms the core of the operating system. It is a program that has complete control over everything else in the system. Now, on most systems, that's the first program that gets loaded on starting up the computer after, of course, the bootloader, so that it's able to actually load anything. The kernel then handles the rest of the startup, as well as the input-output requests from the software. It takes care of the memory and the peripheral devices. Basically, it connects the application software to the CPU, memory, and peripheral devices. The critical code or the kernel is usually loaded into its own area of memory. That area is protected. It can't be accessed by less critical programs. The kernel performs its tasks. It executes processes, manages hardware devices, handles interrupts, and it uses the protected kernel space to do that. What user programs do is they write their text in a text editor, running programs in a GUI. All the user code, user programs are in user space. The separation of the RAM into user space and kernel space avoids the interference of data and kernel, the user data and kernel data, and avoids instabilities and slowing down of the system. It also protects the system from malfunctioning application programs so that they don't crash the entire system. When a process sends a request to the kernel, that is called a system call. Now, the kernel designs differ in how they deal with system calls, how they manage their resources. Monolithic kernels execute all of their operations, all of their instructions in kernel space. This results in operating systems executing relatively fast, faster than the alternative, which is a microkernel, where they use the user space for RAM for their execution. This results in somewhat slower operation, but utilizes less, requires less RAM. Since RAM is relatively cheap, monolithic kernels are most popular. Most kernels control their monitors, input devices, disk drives, peripherals in general, by providing device drivers specific to the individual units. In the end, an operating system is software, a program or collection of programs. And in order to do anything, these programs have to be executed, processed by a central processing unit. They are, after all, just sequences of instructions. The instructions have to be executed. Operating systems, though, are atypical in several ways. one of them, most important, that the operating system programs have to have some privileges not available to normal application programs. For another, they have to relinquish and regain control of the processor frequently, much more frequently than just about any other kind of program. Finally, although they don't execute for a long time at any one point in time, they are executing a lot. Most application programs send system calls to the operating system, and then the operating system does its thing and returns control to the user application program again. But they are executing a lot. Since they're executing frequently, efficiency and reliability are essential in the design. Much more important than just about any other kind of program. If you have a problem with your operating system, it's going to affect all of your user programs. There are some activities that normal application programs, user programs, shouldn't be able to perform. Some areas of memory that normal application programs shouldn't be able to access. Many of our operating system modules have to execute instructions that are not available for application programs. Some modules have to reference memory areas that are protected from normal programs. Some modules have to execute in kernel space rather than in user space. Most modern computers are multiprocessing systems. When an application starts executing, it's the operating system that loads it and transfers control so that it starts executing. When it does this, of course, the operating system has to relinquish control to the application program. Now, at some point, the application program is going to stop executing. It might stop executing because it finished. It might stop executing because it's paused for an input-output operation. It might just stop executing because it's used up all of its time slice. Whatever the reason, when the application program stops executing, control returns to the operating system. An operating system program called a monitor takes up execution, starts executing when an application program stops, finishes. The monitor identifies the process that'll be appropriate to execute in the given situation, in input-output execution, a new application program, whatever, an process to start executing, and passes control to that process. Now, application programs can relinquish control frequently relinquish control and then resume execution later. But very few application programs ever relinquish and begin again, as does any operating system monitor. Very, very few programs execute as frequently as do the operating system programs. That being the case, if there is code that is inefficient, then that inefficiency is going to be executed much more often than other kinds of code. In particular, this is true of the control transfer, since operating system programs regain and relinquish control of execution sequence with great frequency if there is an inefficiency in the way this is done, then that inefficiency is going to translate into a slowing down of the system with much more frequency than does any other kind of program. As just mentioned, operating system programs execute frequently. Since they're executing frequently, if there are any errors in their code, if they're doing things that differently than they were expected to do, then those errors are going to occur much more often than would be occurring with the execution of an application program. Further, application programs depend on the operating system programs in order to function, to transfer control to them correctly, provide them with proper data, to take up execution when they finish, to provide them access to external functions and procedures, to obtain data from external devices, and so on. If there's an error in any of those, that's going to affect the way that the application programs. Finally, since operating system programs can access wider range of memory than application programs, and they can make use of more powerful commands that the application programs don't have available, there's a much greater potential for serious damage by an operating system program than an application program. An application program is generally going to be a resource user, and it's the operating system that has to manage those resources. The computing system is only going to have a limited number of resources: processor or processors, primary storage, secondary storage, peripheral devices, files stored on the secondary storage usually. And your computer system is probably, most modern computer systems will have multiple processes running concurrently. When you have several processors executing concurrently, it's pretty much inevitable that at some point or other, two of them are going to attempt to use the same system resource. And many of the resources can only be used by one process at a time. Somebody has to exercise control over which resources are assigned to which processes. And guess what? It's the operating system that has to do that. Now, there's got to have to be some kind of policy established determining how the decisions are going to be made as to how the system resources are going to be allocated. And it's the operating system has to be written and designed to enforce those policies. Among the factors that have to be considered when designing your resource allocation policies: fairness, responsiveness, and efficiency. They also have to be allocated in a way that will avoid deadlocking and starvation. Now, these factors aren't mutually consistent. Systems designed for some kinds of objectives have different priorities depending on what kind of systems you're designed for. In the context of resource allocation, fairness basically means that resources should be allocated in a way that lets all of the processes proceed, that every process should have a reasonable expectation of getting the resources that they need and getting them in a reasonable timescale. Of course, operating system should be fair. Certainly, your operating system should be designed to avoid starvation. If a process is not going to be receiving the resources it needs, then it shouldn't be allowed in the system to begin with, taking up resources that other processes could use. But reasonable time is subject to situations and interpretations. A batch user might very well expect that getting the results back on the following day is reasonable, but an interactive user is probably going to start getting unhappy after waiting 10 or 15 seconds. So what one kind of users considers fair or reasonable is not necessarily the same as what another user is going to consider fair or reasonable, subject to interpretation. In a time-sharing system with interactive users, resources should be allocated in a way that these online users should have a reasonable expectation of system interaction in what the users would perceive as being reasonable. Again, reasonable is subject to interpretation. In many situations, and for certain kind of processes, 24-hour might be reasonable. Of course, this would only be on a batch system. Today, personal computer systems or interactive systems where most of the users are working online, 10 seconds, the standard originally proposed when Kemeny and Kurtz were designing the first successful interactive multi-user system. 10 seconds is now certainly going to be considered much too sluggish. In the context of resource allocation, efficiency means that resources should be allocated in a way that optimizes their utilization. This factor can be inconsistent with fairness and inconsistent with responsiveness. If it's given too high a priority in its allocation schemes, it could lead to starvation situations. It does, however, have a place in allocation policies, especially in allocation policies and systems where they involve resources that are rare and or expensive. It's in resource allocation that the operating system has to deal with conflicts frequently. When we have concurrent processes executing and both or more than one process requests a given resource, quite possible that the resource has already been allocated to another process. So the process has to wait until the resource has been released. But possible that the first process has been allocated another resource that the second process needs to proceed. So we have process 1, which is requesting resource 2 and has been allocated resource 1. But resource 2 has been allocated to process 2, which requests resource 1. Resource 1 cannot be allocated to process 2 because it's already been allocated to process 1. So process 2 cannot proceed until process 1 releases resource 1. But process 1 will not release resource 1 until it gets resource 2 in order to proceed and terminate. But resource 2 is assigned process 2, which cannot proceed and will not release. So this is a deadlock situation. Neither process can proceed. So neither process will release its resource, the resource it has been allocated. So neither process will ever be able to terminate. Neither process will ever release its allocated. Another kind of problem can occur in a busy system when a process needs a resource that's commonly used and can't get it because other higher priority processes are using it. This is called starvation. The process simply can't proceed because it can't get a necessary process because there are too many other processes with higher priorities. Operating systems have to be designed to identify possible deadlock or starvation situations, prevent them from happening, and if they do occur, recognize that they're happening and deal with it.